The battle between stable and unstable sorting algorithms in modern programming. Sorting algorithms form the backbone of efficient data processing in computer science. Whether organizing arrays, managing databases, or optimizing search operations, choosing the right sorting technique can significantly impact performance and correctness. In particular, understanding the distinction between stable and unstable sorting algorithms is crucial for developers working with complex datasets. This guide dives deep into these two categories, exploring their characteristics, applications, and trade-offs in real-world scenarios. Understanding stability in sorting algorithms. A sorting algorithm is classified as stable when it preserves the relative order of equal elements during the sort process. For example, if two items have identical keys but different original positions, a stable algorithm will maintain their initial sequence after sorting. This behavior matters significantly in situations where secondary key comparisons are required. Imagine a list of students sorted by exam scores. Stability ensures that those with the same score retain their alphabetical order from the original dataset. Conversely, an unstable sorting algorithm may rearrange equal elements arbitrarily, potentially altering their original order. While this might seem problematic at first glance, certain optimization scenarios actually benefit from such flexibility. Recognizing stability requirements upfront helps avoid subtle bugs that could arise from unexpected reordering in complex systems involving hierarchical data structures. Distinguishing features of stable and unstable sorts. To better appreciate how these sorting mechanisms operate, let's examine several fundamental differences. Order preservation. Stable sorts guarantee consistent ordering for equivalent elements, unstable sorts do not. Data dependency. Stability often depends on additional information beyond primary comparison keys. Implementation complexity. Maintaining stability generally increases code complexity compared to non-stable alternatives. Performance implications. Some stable algorithms require extra space or time overhead for maintaining order. These distinctions highlight why some algorithms remain popular choices while others find specialized niches within specific application domains. Common examples of stable sorting algorithms. Several well-known sorting techniques fall under the category of stable algorithms. Among them, merge sort stands out due to its inherent stability properties derived from dividing and conquering strategies. Merge sort guarantees stability through careful merging phases that respect existing element orders. When combining subarrays, elements with equal values always preserve their original positions from before the merge operation. Bubble sort also demonstrates stability by repeatedly comparing adjacent elements without disrupting the sequence of duplicates. However, its quadratic time complexity makes it unsuitable for large-scale datasets. Timsort, developed specifically for Python and Java environments, leverages both insertion sort and merge sort principles while ensuring stability across diverse input types. Insertion sort maintains stability naturally since it builds up the final array incrementally by inserting each item into its correct position relative to already sorted preceding elements. Famous instances of unstable sorting algorithms. Quicksort provides a prime example of an unstable sorting approach. Its divide and conquer methodology involves partitioning arrays around selected pivot points, which can lead to unpredictable rearrangements among equal-valued elements. Despite being highly effective for average case scenarios, Quicksort's instability means developers must carefully consider whether they need to preserve original ordering relationships within duplicate entries. Heap sort represents another classic case of an unstable algorithm. It organizes elements into a priority queue structure and extracts maximum/minimum values iteratively, an approach that doesn't inherently protect against reordering of equivalent items. Radix sort exhibits instability depending on implementation specifics, particularly when using least significant digit-first approaches versus most significant digit-first strategies. Evaluating performance trade-offs. When selecting between stable and unstable algorithms, developers must weigh various factors including time complexity, memory consumption, and practical application needs. Time efficiency remains a critical concern, especially with large datasets where even small improvements matter significantly. Quicksort typically outperforms merge sort in terms of average execution speed despite lacking stability. Space complexity considerations differ substantially too. Merge sort requires O(n) auxiliary space, whereas quicksort usually operates in place with only O log n stack usage in the best cases. Memory constraints heavily influence choice selection, particularly for embedded systems or mobile development where resource limitations impose strict boundaries on available storage capacity. Applications driving algorithm selection. Certain industries rely heavily on stable sorting for mission-critical processes. Database management systems frequently employ stable methods when handling multi-column indexes requiring predictable ordering results. E-commerce platforms utilize stability features extensively during product catalog updates to ensure consistent presentation of similarly priced items according to date added, brand reputation, or other secondary criteria. Social media networks prioritize user experience consistency through stable algorithms whenever displaying news feeds containing posts with identical engagement metrics. Financial institutions depend on reliable sorting mechanisms for transaction records and audit trails where maintaining chronological integrity prevents potential compliance issues. Implementing stability mechanisms. Many modern languages provide built-in support for stable sorting implementations. Python's sorted function uses timsort internally, ensuring stability while maintaining high-performance characteristics suitable for diverse inputs. Java offers similar capabilities via the arrays.sort method for object arrays, automatically applying stable sorting based on defined comparator logic rather than natural ordering alone. When developing custom solutions, programmers can implement stability manually by incorporating additional fields indicating original indices alongside main comparison keys during sorting steps. Some frameworks allow specifying custom comparators that include tie-breaking rules while still preserving overall stability attributes expected from standard library functions. Advanced considerations beyond basic classification. While distinguishing between stable/unstable classifications forms foundational knowledge, advanced practitioners explore further dimensions influencing algorithm effectiveness. Hybrid approaches increasingly combine elements from both paradigms, leveraging strengths of different methodologies based on current workload patterns observed dynamically during runtime executions. Adaptive algorithms detect internal structure qualities present within input sequences and modify their behaviors accordingly. This includes detecting pre-sortedness or partial orderings that suggest minimal changes required. Persistence requirements add another layer of complexity when dealing with continuous data streams needing persistent ordering maintained across system restarts or distributed computing contexts. Navigating practical implementation challenges. Real-world coding encounters reveal many subtleties affecting successful deployment of chosen sorting techniques. Developers should be aware of common pitfalls associated with implementing either type effectively. Lack of clear documentation regarding an algorithm's stability status often leads to unexpected surprises when migrating legacy codebases towards newer technologies featuring changed default behaviors. Incorrectly assuming implicit stability guarantees across different language libraries can result in hard-to-trace errors manifesting later during testing phases or production deployments. Varying hardware architectures introduce additional variables impacting actual runtime performances, making benchmarking essential prior to final decisions involving large-scale projects. Future trends shaping sorting technology evolution. Ongoing research continues pushing forward innovations aimed at improving both traditional and emerging sorting methodologies alike. Current efforts focus largely on adapting classical concepts for parallel/distributed computation environments. GPU utilization enables massive concurrency gains by offloading computationally intensive parts onto graphics processing units optimized for vectorized operations typical in matrix-based computations. Quantum computing introduces entirely new mathematical models challenging conventional assumptions made previously about computational limits imposed by physical realities governing classical processors. Machine learning integration promises novel ways of predicting optimal parameter settings dynamically adjusted based on characteristics detected within incoming datasets rather than relying solely upon static configuration files. Conclusion: mastering the nuances between stable and unstable sorting algorithms equips developers with vital skills necessary for constructing robust software systems capable of efficiently handling complex data challenges. By thoughtfully evaluating application-specific requirements alongside technical trade-off analyses, professionals can make informed decisions leading toward consistently high-quality outcomes regardless of project scale or domain specificity involved.